Hi friends, so we are into our third lecture of risk conscious operations management of complex engineering system, and the topic of this week is dependability engineering. In previous lecture we saw series configuration, parallel configuration, component reliability and all, and the fundamental aspects. Now in this lecture we will be talking about, or we will be dealing with standby system reliability. Like parallel system, standby system is a special class of system. As you saw in parallel systems, till the last component operates, your system is success, and system fails only when the last component out of n component fails. If there are two components, both the component failure is a failure of the parallel system. But in standby system, even though it is another form of parallel system, but here there is a combination, like 2 out of 3 component failure or success make the system failure or success. We'll deal with these things. So why these things have come? Parallel system, you are operating other components in a hot standby mode. So it is not preferred when it comes to a practical life situation, and that's why standby systems are there. There are many advantages with standby system configuration. Okay, I am Professor Prabhakar V. Vardhe, and CEO and Director of ERMC Engineering Risk Assessment and Management, and guest professor at Luleå Technology University, Sweden. And of course, I had almost like 35 years or more than years of experience at Bhabha Atomic Research Center, and I retired from there as Associate Director Reactor Group and Senior Professor Homi Bhabha National Institute. So let us start. Okay, so I give you background of parallel system, and of course we had this series system also. Now we will discuss the standby system, and as we go through this presentation, we will be understanding what it means and how it is advantageous and superior to parallel systems, parallel configuration I would say, and then we will derive an equation for standby system, standby and redundant system. Okay, and finally we will be discussing availability aspects also, and then relevance of availability in risk analysis, because there is a concept of demand failure probability, which is also referred as availability, because passive systems, that let's say electronic board, if any failure has occurred and it is a safety system, it is a part of a safety system, we may not know. So the failure remain passive, but the moment when demand is generated, system will not come, or it will not get actuated. So that is called demand failure probability, also form part of availability. Then we have operational availability, uptime, downtime, and role of common cause failure in modeling this availability. We have seen earlier also in this configuration. We will try to introduce this concept here also and see how it impacts adversely the system reliability or availability. So we saw parallel system configuration. All the units were operated in parallel and catered to meet the requirement. Even single unit operation can assure. So we understood, because other units are operating as a hot standby mode, and hot standby mode means they are operating, but they are not active in terms of generating the you can say benefit, like it is a cooling system or anything, and the moment the other operating system fail, these units they start meeting the function. So this is called parallel configuration. But the name of the game is all the unit failure leads to system failure. But and there was no switching device. All the units are operating in parallel. So one the operating unit has failed. So the parallel unit is there to meet the function. But when we talk about the what is the disadvantage with this kind of system? It is resource consuming. You are operating this system in a hot standby mode, parallel units. It is and then it is causing aging also of the components. Okay, and not a good example from maintenance point of view also, because all the units are operating. So how to do the maintenance and all? So there is something called standby redundant configuration which is there. So here we have this standard. So let's say try to understand this whole thing by example of two pumps which appears to look like be operating in parallel, but that is not the case. There is a switching system in between. So first let us say pump 1 is operating, the pump 2 remains shut down, unlike parallel systems. Okay, and when pump 1 fails, the signal goes and then switching system starts pump 2 and then caters to the demand. Okay, so this is what the system is. So you can see in this kind of thing, it is an example of K out of N. So there are two pumps, and how many pumps are required to for the system to fail or to success is called. So out of 2, 1 pump is required for the success. So K out of N. So 1 out of 2 configuration. When there are higher level of redundancy, then out of 5, if 2 pumps are operating, so 2 is K, 5 is N. So 2 out of 5 configuration, this type of systems they are called. And then other first component is operating, other component remains in standby mode. So here we are trying to understand that when the system occurs. So now this particular point I would like your attention, because finally in reliability analysis, what is the system failure criteria? That is the governing requirement which decides for what configuration you want to assess a particular hardware or software configuration. Let us say failure of in reliability analysis there are two ways to, if I am doing reliability assessment, then I will look for system success. That I can say here, as long as 1 pump is operating, this is my system is success. Okay. Now, what I am saying in short is, if 2 pumps operate, 2 out of 2 operate, it is a failure criteria for me. So same configuration I have given the name. So I have to define success as well as failure. Let us say there are 5 units total in the system. So if 2 out of the redundant unit, how I can talk about success and failure? The failure criteria is 4 out of, if I require 2 pumps as for my success, then 4 out of 5 we have to. So like if we go, then the failure criteria is 4 system we have to fail. Okay, 4 redundant component have to fail. Then only it will be called as the success criteria is 2 out of 5 is success and 4 out of 5 is failure criteria. Same numbers we have done. So if the success is 2 out of 5 success and 4 out of 5 is failure for this redundant configuration. Now it is up to you which terms you want to talk about. So here the reference condition was, we require minimum 2 units operating. 2 units operating. So 2 unit operating means 2 units are required for success of the pump. So the moment the moment is 3rd unit is failed. So there are total 5. So out of 5, if 4 out of 3 failure criteria becomes 4 out of 3, because now you don't have 2 units available to you. Success is 2 out of 5 is success. That means any 2 combination they operate. I want your attention on this, how from the same number of units you can work out the failure criteria, success criteria, given what is success and given what is failure, for the system. The redundant system configuration is expressed by k out of n redundant configuration, Sometimes they are called k out of n, sometimes they are called redundant systems also, or standby redundant system also. Okay. Now, if I have to derive an equation for or a formulation for standby system, let me take this example. Switching system is there. There is input, there is output. So reliability block diagram again. Pump 1, pump 2, they are there, and both the pump failure, that is pump P1 and P2 failure, lead to system failure. Okay. Now, operation reliability configuration, the reliability of the 2 unit system can be as follow. Either the operating pump successfully perform for the lifetime of the for the mission time, or the first unit fail and the second unit start successfully, okay, or the standby unit has not failed in standby mode and start the. So this unit will start only when it is not failed in the standby mode and the switching system was performing correctly. So and what is the requirement? Minimum 1 unit is required for success of the system. Now for this configuration, I have to derive an equation for reliability. Then how I go about? Okay. So you saw that P1, P2, they are connected through a switching system, and so initial condition, let us assume here that pump 1 was operating. If I have to do analysis reliability modeling for this system, so at time t is equal to 0, P1 was operating. So what is the situation? Either P1 will meet the complete requirement, mission time requirement, or pump 1 fails and pump 2 takes over, and that will only happen when P2 was available during standby condition, and the switching system was able to send the signal to pump 2, and this particular information will help us in working out the formulation. So let us see what are the notation. The R1T is the reliability of pump 1, okay, for a mission time T. Lambda 1 is the failure rate of pump 1. Now F1T is the probability density function for unit 1, because we are considering also pump 1 failure. So F1T, this you must remember, failure density function, probability density function or failure density function are the basics to describe a distribution, okay, in reliability engineering. So F1T is the PDF, it is called probability density function for unit 1. Switching reliability up to time t, because if the switching system is t dash, so this is switching system reliability, this is pump number 2 standby system reliability in a standby mode, okay, and R2, that is for second pump, reliability of unit 2 for this duration, that means from t dash to t. So this is the configuration. Now let us formulate what we qualitatively we discuss. So for system reliability, it should be RS, system reliability, either the pump 1, that is R1T, R1T is pump 1's reliability, either the pump 1 operates for the mission, or the pump 1 fails 0 to t, F1T dash dt, okay, and switching system is reliable and pump 2 is standby reliable up in standby condition, and then for the second thing, pump 2 is able to meet the mission up to from time t minus t dash, this thing. So I think it is very easy to understand this particular formulation, okay. Now let us go ahead and try to see how it looks like when we okay. So here we assume that it is an exponential distribution. Exponential distribution is simple. We can see, we know that expression for reliability for pump 1 is lambda 1 t, okay. But for pump 1, that is pump 1 failure rate, and then pump 2 pump 1 failure rate, and this is reliability equation for pump number 1 plus. So this happens, pump 1 fails, that is a lambda 1 exponential minus lambda 2 lambda 1 t, that is for pump number 1. This is a PDF function for pump 1. If you integrate, you get the cumulative distribution function, and exponential switching system reliability into switching standby system reliability for pump 2, okay, into then pump operation for a mission of t minus t dash dt. I think up to here everybody. Now the remaining thing is only simplifying the equation and trying to see how we can make it simple by putting some parameters. So performing the integration of the for rearranging the function. So if we do the integration for this component, so this term remains first term, that is for pump number 1 reliability remains same, plus if we perform the integration, we will get this term, and there is a common element 1 minus exponential, and all system failure rate, that is lambda 1 failure rate, lambda 2 failure rate, pump 2 failure rate, lambda switching system reliability, and lambda, because they are basically all add up of the failure rate, that will give us this term. So this is the failure probability of this. Now to simplify the above equation, let us say if switching system failure rate and standby system failure of the pump are 0, then you put this value 0 and you will get reliability for system reliability for this pump for this pumping system, standby redundant system is equal to exponential, this term remains as unit, lambda 1 by lambda 1 minus lambda 2, and then remaining equation here. Now to further simplify it, if I say my pump 1 and pump 2 failure rates are same lambda, so it gets further simplified. So reliability is nothing but exponential minus lambda t plus lambda t exponential minus lambda t, and here we can take out this 1 plus this exponential lambda t term common. So we are left with 1 plus lambda t, and this is a final equation for standby redundant system reliability. Okay. So probably with a different combination also, so we should be able to solve this equation, but it gives a better understanding how to account for switching system, how to account for standby pump reliability, how to account for the reliability for a given or I can say residual period when it has to complete the mission. Okay. So these kind of factors, and we have simplified this equation, but we can do if you write a small computer program, we can factor in switching system, we can factor in other things also, so pumps and all in their different modes of operation, and we can get the system reliability for a standby mode. So though we have solved the equation, but as the number of redundant component and their combination, like suppose if I have 2 out of 9 system as the success criteria, so 3 out of the 9 will become the failure criteria. This kind of situation we should be able to handle, and then the components are more, so this problem also will become complex. Okay. So now we have compared this standby system with the parallel system, and arguments for standby system. If you look at the common approach in standard industry, they go for standby system reliability or K out of n configuration, because there is a, not that they are compromising safety, the failure rate in standby mode are lesser compared to the operating mode, because there is no aging, but still there can be passive failures in industry we encounter, but then other factors like economics and maintainability, those things they come into the picture. So 2 out of, and then in 2 out of n there is a better maintainability for standby system. You can perform maintenance and make it available, you can check it and all that, and in standby system also often the testings are done. So, this testing they provide you a required you can say model for ensuring the reliability. So, so that is one reason why standby systems are, and we have derived the equation for standby system K out of N system reliability. We have considered two pumps. Initial condition was pump 1 was operating, pump 2 was in shutdown state, and it was to come based on the switching system demand.